Good afternoon to all of you. So, we are on the third day of the course. Hope you are enjoying. And on the third day, we'll be discussing on advances in thermal and microwave remote sensing techniques for geological applications. So, to begin with, thermal remote sensing and a bit introduction. The electromagnetic wavelength region of 3 to 35 micrometer is popularly known as the thermal infrared region. And for geological remote sensing, particularly over the Earth, we use the 8 to 14 micrometer range, and there are certain reasons. So the reasons as follows: that at ambient terrestrial temperatures, you know what is the temperature? Ambient temperature is 25 degrees Celsius. So the peak of the Earth's blackbody radiation, it is around 9.7 micrometer. Okay, so 9.7 micrometer, you see, it is more or less at the center of 8 to 14 micrometer range. Okay, but most important reason is there is the excellent atmospheric window that is available at 8 to 14 micrometer. Just see this illustration below, and you see here on the y-axis, this is the atmospheric transmittance, and on the x-axis, it is the wavelength in micrometer. Now you see, this is the visible region, so 0.4 to 0.7, then it is near infrared, then shortwave infrared, isn't it? And if you come to 3 and above, then it comes under the thermal infrared. See here, there are the atmospheric windows. That means the atmosphere is transparent to a great extent in 3 to 5 micrometer and also 8 to 14 micrometer, isn't it? But if you see 8 to 14 micrometer, there is this gap here, 9 to 10. And you know why? Because there is the ozone layer, the Earth's ozone layer, that absorbs much of the thermal energy between 9 to 10 micrometer range. Okay, so what you see here, in thermal region, there are 3 atmospheric windows, and most important one is 8 to 14. Then 3 to 5 is another window, is also quite good. But if you see, this is the 17 to 25 micrometer. This window is quite subdued. It's a very small atmospheric transmittance, isn't it? And see here that because of the ozone layer, in satellite-based thermal remote sensing, we cannot use this 9 to 10 micrometer. So we prefer to use from 10 to this 12. That means 10.5. You can see here 10.5 to 12.5 micrometer. This is the range we use for spaceborne thermal remote sensing. Whereas for airborne, there is no question of ozone layer because it is much below the ozone layer. So we can use, in case of this 3 to 5 micrometer, and in case of these airborne sensors, as well as the entire 8 to this 14 micrometer, because ozone layer problem is not there in case of airborne sensor. But in 3 to 5 micrometer, you see, there is another problem. The problem is 3 is this is the upper limit of the optical region, and optical region, there are a lot of this reflection takes place. So during the daytime, what will happen? You will have reflected this signal also. So there will be mixing of these solar reflectance, that means reflected energy, with the emitted energy or the thermal energy. So if you go for this region 3 to 5, there will be this kind of mixing problem. In that case, if you go for this nighttime thermal imaging, then absolutely fine. In fact, for this also, if you want to study these in situ, these inherent properties of rocks, okay, or your thermal source, means heat source in the Earth other than the solar radiation, then you should go for the nighttime thermal imaging, nighttime thermal remote sensing. Okay? In fact, pre-dawn thermal remote sensing is the most important one, because in that case there is no solar radiation effect, will be negligible. Now coming to this thermal remote sensing of the sun and the Earth, if you see here in the illustration on the left side, you see this is the solar radiation spectrum here, and this, it is given in the yellow shade. Okay, and this is top of the atmosphere, this solar radiation spectrum. But if you see this your solid, this your the black line, okay, that is basically your spectrum of the black body at 5 to 50 degrees Celsius. So what you see here is the solar radiation spectrum and the top of the atmosphere, and this black body spectrum at 5250 degrees Celsius, they are very much in agreement. They are very close to each other. What does that mean? It means that the temperature of the sun is very close to 5250 degrees Celsius. Right. But if you go down to the sea level, that means on the Earth's surface, then you see this your thermal radiation spectrum. Okay, this your something like this, the radiation spectrum. Okay, something like this in red color. Okay, so here you see the difference from the yellow to red, and there are some this your absorption, this your patches also, absorption peaks also. So why it is happening? Because in the atmosphere there are many gases, there are aerosol particles, essentially these your water vapors, carbon dioxide. Okay, so these are the gases, and including this oxygen also. Okay, so these gases makes this difference. They absorbs this radiation. Okay. Now you see in case of sun, if you see this radiation spectrum, the maximum radiation happens at 0.5. That means at green band. Okay, green band is approximately 0.5 to 0.6 micrometer. But if you see in case of the Earth, this maximum radiation peaks at 10 micrometer. That is 9.7, as I have already discussed in the previous slide. So if you want to do thermal sensing of the sun, then which area is important to us? This is the spectral band in and around 0.5 micrometer. Isn't it? Because that is the maximum radiation peak. In fact, if you see that this solar spectrum, that 0.4 to 0.7, that is in the visible region, it includes almost the half of the spectral radiation, okay, from the sun. Whereas in case of Earth, the maximum radiation happens in and around 10 micrometer. Okay. So now this basic principle of thermal remote sensing, it is basically governed by the Planck's function and Planck's law. Okay, and what is this Planck's law? It is the relationship between your radiant energy, okay, between radiant energy and the kinetic temperature of the material and the wavelength in which the radiation takes place. Okay, and this equation, if you see it carefully, L lambda is the spectral radiance that is in the band in and around the lambda. So this is the spectral radiance, and it is related to what? It is related to say 2 pi. Yesterday was a pi day, isn't it? What is it? It is a constant 3.14. Then h is a Planck's constant, and c is the speed of electromagnetic radiation. Okay, so these values are known to us. Then what is a variable? Lambda, where this radiation takes place. And what else? The temperature. What is the temperature of the object? So if you get the spectral radiance, from that you can get the temperature. And this particular relationship holds true for this black body. Okay, where this thermal emissivity is considered to be 1. What is thermal emissivity then? Then we'll discuss. Thermal emissivity is the ratio how much your thermal energy or solar radiation the material receives and how much it emits, this ratio. Okay, in fact it is just the reverse, how much it emits divided by how much it has received. If the two values are same, then emissivity will be equal to 1. In case of black body, it is 1. Okay, so that is why it is this relationship like this. But if you consider in case of terrestrial body, where the spectral emissivity is not 1, then you have to put this value. Okay, epsilon lambda, that is the emissivity at an wavelength lambda. Other than this, all this your expression is same. So you can understand here that from this Planck's law, we can have this temperature of the object from this emitted energy. Okay, if you know that how much energy it is radiating in a particular wavelength, okay, and what is this wavelength value, then we can get what is the temperature. So for that we have to rearrange this equation, isn't it? Now you see, in case of thermal remote sensing, there are certain physical properties, and these physical properties are important for thermal sensing of the Earth's surface, isn't it? So these physical properties are governed by certain parameters. These parameters like thermal conductivity, then this density of the material, then your thermal diffusivity, and most importantly thermal inertia. Okay, thermal capacity is basically a combination of two. It is a product of the density and thermal conductivity. Okay. Now thermal inertia is very sensitive and it is very much different for different rock materials, and that can be used for characterize the different terrestrial rock materials. Okay. And then what is thermal inertia? That we need to understand. Thermal inertia is similar to this moment of inertia. So how far it resists with the supply of this your heat energy. If you supply some heat energy to a particular terrestrial object, terrestrial body, some certain rock materials, then how far it resists to change the temperature. So if you supply it, then it will try to increase the temperature. Then the thermal inertia is basically, it tells you that how much it resists to increase the temperature. So if the thermal inertia value is high, then it will resist high. Okay, it will resist more. So it will not allow the temperature to increase. But on the other hand, if the thermal inertia value is low, then what will happen? The resistance will be low. So if you supply it, easily its temperature will increase. If you extract it, easily the temperature will go down. The temperature will decrease. And this, the formula is something like this. Thermal inertia is equal to square root of K, rho and C. And K, you know what is K? K is the thermal conductivity, rho is the density, and C is the specific heat. But this is you need to measure in the laboratory, because for measuring thermal conductivity you need to measure in the laboratory only. Rho, density, also you have to have certain this your system, and C again specific heat, isn't it? All you can measure in the laboratory only. So it is very cumbersome process. But there is this your remote sensing based approach is there, where we can measure this thermal inertia, and which is known as apparent thermal inertia, ATI. Okay, and this value is very close to this actual thermal inertia. Not exactly the same, but it is very close to the actual thermal inertia. And what is the formula? You know, this is 1 minus A divided by delta T. What is 1? 1 is the total energy. You know these energy balance equations, no? Kirchhoff's law, First law. This, it is total energy what is incident on any object is equal to what? Total energy incident on an object is equal to reflected energy plus transmitted energy plus absorbed energy, isn't it? So if you divide this total energy on either side, then what will happen? Total energy divided by total energy will become 1, and on the other side, reflected energy by total energy, transmitted energy by total energy, and again absorbed energy or energy divided by total energy. These will be the ratios, and they are known as reflectance, transmittance, and absorptance. Now you see the total energy which is incident on any object. Okay, so here the major part is reflected. Whether it's major and minor, that again depends on the material property. Essentially the color of the material. If the color of the material is white, for example, then the reflection will be very high. But if the color of the material is black, then it will absorb, isn't it? So the reflected energy is the one component which is coming out of the system, and then there are two other components. One is the transmitted energy, which is going inside the material, transmitting inside the material, and another component is how much the material absorbs, is the absorbed energy. So if you do this 1 minus A, that is A means reflectance or albedo, okay, then what you basically you are here, it means that your transmitted energy and absorbed energy, these two things are going inside the material, and they both are responsible for increasing the temperature, isn't it? Because the heat or the solar radiation, it is going inside the system, either in terms of transmitted energy or in terms of absorbed energy. So 1 minus A means 1 minus reflected energy, means this energy which is going inside the system to raise the temperature. Similarly, if you extract this heat, then it will try to decrease the temperature. That is the other case. So 1 minus A That means this total energy minus the reflected energy divided by delta T. So how far, if you supply this much energy, then how far this temperature of the object changes, increases. So if you have the temperature during your midday or noon, okay, that is the highest temperature possible for the material. And if you take the temperature on the midnight, that is the lowest temperature of the material possible because of the solar radiation. Okay, so if you have the delta T temperature change, then what will happen? It gives you the resistance, isn't it? The energy available to the system or to the material to change the temperature, and how much temperature changes. So that ratio is in fact tells you the thermal inertia. This thermal inertia is very important for characterizing the geological materials. Okay, that I have shown in the previous slide how thermal inertia are different for different rock materials. Now coming to the another thermal this property, that is the emissivity. Emissivity, you see, in case of black body, that is the ideal concept, no, black body. In case of black body, whatever the energy is available to your body, whatever is incident on the body, okay, so this is the entire energy is absorbed, and after that what happens? Entire energy, what is absorbed, it is emitted or radiated. So emissivity for a black body is what? This is how much energy is radiated divided by how much energy is absorbed, received. And because in case of black body, these two, the magnitude are same, the energy received and energy radiated are same, then what will happen to the ratio? The ratio will be 1, isn't it? But in case of terrestrial body, it is not the case. In case of terrestrial body, the energy what is received, the entire energy cannot be radiated. It radiates the major part, but it does not radiate the full. For example, it can radiate 90%, it can radiate 95%, it can radiate 80%, 85%, something like this. If it is so, then what will be the value of the EPSA, emissivity? It will be this, what is radiated by what is received, it will be around 0.9, 0.95, isn't it? 0.8, 0.85, something like this. Okay, this is what is the thermal emissivity means. And it is wavelength dependent. That is why it is R lambda by B lambda. There is another relationship by which also you can have thermal inertia value at a particular wavelength range. This is your emissivity is equal to TR, that is the radiant temperature, and divided by the kinetic temperature to the power 4. And what is radiant temperature? The temperature what you can get by Planck's law from the radiated energy. Okay, from the spectral radiance, what is the temperature you can estimate by Planck's law? Assuming this thermal inertia is 1 and Tk is actual temperature. So you understand this temperature what you can get from this relationship will not be same as the kinetic temperature. It will be lesser than that. Okay, so Tr will be lesser than the kinetic temperature or the actual body temperature. Okay, so Tr by Tk to the power 4 will be less than 1, isn't it? So this is how also you can get thermal emissivity. Okay, these are some of the basic principle. I am not going to the much basics, but I will discuss more on the recent advances. Okay, what advances in terms of the data availability, what are the new missions we have now, how thermal remote sensing is more feasible nowadays, and what are the different applications we can do, what are the advancement in the thermal remote sensing data analysis techniques. So those things I will discuss now. So to begin with, what are the present day thermal sensors? Okay, like for example AVHRR NOAA. Okay, so this data is available for decades, but here the problem is here the spatial resolution is coarse. It is almost 1 kilometer instantaneous field of view, IFOV, 1 kilometer. There is another problem here. This you can see here, these anomalies must have temperature in excess of 1000 degree. Why? Because data also be used to sense and monitor high temperature objects such as volcanoes. Okay, here problem here is quantitative analysis of these targets may not be possible due to the dynamic range setting is a problem for these sensors. Okay, so essentially due to the coarser spatial resolution, and this your dynamic range of the this your data. So this is not always very good for thermal sensing of the this the subtle temperature change, but for high temperature objects it is fine. Now going to the MODIS, moderate resolution imaging spectroradiometer, that is MODIS. Okay, this is under this US mission. So here this is much better than this you know IIRS, but here also your spatial resolution is also 1 kilometer. But in case of this this MODIS, you have the Terra MODIS and you have the Aqua MODIS. Terra MODIS is for the purpose of this thermal sensing of the land, and Aqua MODIS for the water bodies. But essentially these two satellites, okay, it is acquiring data over the land maybe around 10:30 or so during daytime, okay, and again night time at 10:30, that is by Terra MODIS, and Aqua MODIS around 1:30, and again 1:30 in the night. Okay, so you have 4 this your times you can have data over the same area. So daily temperature you can have. Not only that, you can have temperature during this daytime, and you can have temperature during night time. Now there is another mission, that is the SNPP IIRS, visible and infrared imager and radiometer suite. Okay, so here this advantage is spatial resolution is much finer, around 375 meter is the pixel size here. Okay, and then comes this ASTER, advanced spaceborne thermal emission and reflection radiometer. Here this is spatial resolution is 90 meter, but the most important advantage of ASTER is that it is multispectral, the number of bands. This is also available in case of IIRS, in case of MODIS, in case of IIRS. These are multispectral bands. But if you go to the this Landsat TM or Landsat ETM plus, then in that case there is only one band. Thermal band is one, that is band 6, but there are sweet bands that can also be used for high temperature object mapping. Okay, so you see in case of this Landsat TM and ETM plus, here the this your thermal band has a spatial resolution of 120 meter and ETM plus has 60 meter, and here the spectral band is 10.4 to 12.5, only one band. But this later Landsat this your sensor, that is Landsat 8 TIRS, I'll discuss on that in the subsequent slide. There we have 2 spectral bands. In case of IIRS in NOAA mission, so there are 3 thermal bands. One is 3.55 to 3.93, another is 10.5 to 11.5, and another is 11.5 to 12.5. Okay, it's another mission. This is old one, 1978 to 1980. This is heat capacity mapping mission. Okay, so there are 2, this your band 2, one band only. Okay, and 10.5 to 12.5. Here the spatial resolution or pixel size was 600 meter. This is old one. But if you see the present thermal sensors, then your MODIS, as I have already discussed with you, there are the 31 and 32. These are the 2 bands we are very much using for surface temperature. But there are other bands also. Okay, you can see 8.4 to 8.7, 9.5 to 9.8. But this is not important for thermal sensing of the Earth surface, because this is for ozone sensing. Okay, and there are bands here also. See, from 3.5 to 5 micrometer, there are also number of spectral bands, but they are used for different purposes. For surface temperature, we can use 10, 20, 21, even 22, 23. These bands we can use. Okay, and 31, 32 essentially we can use for in the thermal remote sensing range. But here the spatial resolution is 1 kilometer. And as I told you, in case of this your ASTER, there are many bands. In fact, there are 5 bands. So these are named as B band 11, 12, 13, 14, and 15. And you see the spectral bands. Okay, 8.125 to 8.475. Similarly like this. And finally it is 10.950 to 11.650. And spatial resolution for all is 90 meter. Okay. Now see, in case of this Landsat TM bands, as I have already this told you, that is 10.4 to 12.5 micrometer. And in ASTAR it is something like this. There are 5 bands, and here there is no band because there is ozone layer. And then if you go to the Landsat 8, this is the IIRS sensor, then there are 2 thermal bands instead of 1 in case of Landsat TM and ETM plus. So 10.3 to 11.3 and 11.5 to 12.5. And here the ground resolution is 100 meter. Okay. Now coming to these features, these your sensors, that one is geoimaging satellite or GISAT. That is one very important mission, and it is scheduled for launching from ISRO. Okay, so it is known as geoimaging satellite. It carries the geoimager. So here there are visible near infrared, then there are thermal infrared bands, and you know here the thermal infrared bands with a resolution of 1.5 kilometer special resolution. So those things are not very great, but what is great, you know, it is the sensors is placed in a geostationary orbit, because GISAT is a geostationary satellite. It is not a polar satellite. So that means it will remain fixed with respect to your Earth surface, and it will be covering the Indian continent area. Okay, India and surrounding region. Always it will be focusing on that. So continuously it will observe the Indian territory. Okay, so by this mission, what is the purpose? So here sector wise we can have your image in 5 minutes, but on an average in every 30 minutes we will have image of the entire Indian subcontinent. We can have thermal image also. Okay, for that your time may vary, and the spatial resolution will be 1.5 kilometer. Now this one of the very important future thermal this mission is known as the Trishna. And Trishna, you know, it is the acronym of Thermal Infrared Imaging Satellite for High Resolution Natural Resource Assessment. It is an Indo-French joint mission and planned for launching in the end of 2024 or 2025. Here there are visible bands, there are NIR bands, there are SWIR bands, but what is most important to us, there are 4 thermal bands. Multispectral thermal remote sensing is possible, and the uniqueness of this mission, you see, there are 4 bands. Pixel size is much better. Instead of 90 meter in case of your ASTAR, it is 57 meter to 90 meter definitely. But in case of deep sea, it is 1 kilometer again. But what is the unique your property of this mission is the swath. In case of ASTAR, the swath is only 60 kilometer, but here you see it is 1026 kilometer swath. It will cover this much area. So that means repeatability is very close. And this is the purpose. This is the research focus. So what are the research areas? Ecosystem water stress and water resource management, hydrology, urban heat island, cryosphere, atmosphere, and many other high temperature, this object detection and spatiotemporal dynamics of these thermal anomalies is the purpose of this mission. Now you see this slide, perhaps we have already discussed yesterday. See this same area, how it looks on your optical multispectral pulse color composite. Here you see it Landsat TM pulse color composite or FCC 754. Here there are basically 3 broad rock types are there. One is the dark volcanics. These are the dark areas. Okay, these areas. And then there is the limestone, highly reflecting limestones. And in between, this is the little brown. These are the altered these products, altered rocks. Now you see in case of thermal image, that is Landsat TM band 6, this your appearance or their brightness is just the opposite. Limestone, where the maximum brightness is there in the optical region, maximum reflection in optical region is dark. Why? Because where the reflection is more, there will be absorption will be less, and if absorption is less, radiation will be less. And in thermal image, what you are measuring? You are measuring how much energy is emitted, how much energy is radiated. So that is why it appears dark. In case of optical image, it appears bright. On the other hand, if you see these dark volcanics, those are dark in the optical image, and here you see these are all bright. Okay, so this is how it varies, and altered zones is intermediate in its tone. Now see, this is the recent your advancement, that thermal remote sensing is not only for this your temperature detection, isn't it? Thermal remote sensing is can be used for based on the thermal inertia, definitely, but single band or monochromatic thermal band is not the answer for geological remote sensing. Then what we should go for? We should go for multispectral thermal imaging, and from this multispectral bands, similar to optical false color composite, we can generate false color composite from the thermal images, because they are spectral bands in different wavelength range. See, this is an example of these airborne teams. Since this your sensor, that is from NASA JPL. Okay, there are 6 spectral bands similar to ASTER, except here because it is airborne, so there is one band in the this ozone range also is available here, 9.4 to 10.2, which is not available in case of ASTER, because ASTER is placed in a satellite, and satellite is above the ozone layer. So this thermal radiation, it will be absorbed by the ozone layer, and you will not get anything from the sensor. But in case of airborne sensor, it is below the ozone layer, so you can have this band also. Okay, so there are 6 bands. Now out of the 6 bands, you see, if you generate an FCC using 531, then what is going to happen? You are getting a color image. Why color image? Because different materials have different thermal inertia. You see, this is the alluvium, no? Why? This is alluvial fan. So alluvial fan area, the material is loose. Material is loose, material is unconsolidated, the density is much less. Then what will happen? Your thermal inertia will be very low. Okay, because thermal inertia is what? Square root of K rho C, specific heat and density. If these values are smaller, then thermal inertia will be smaller. So if the thermal inertia value is smaller, then what will happen? It will change the temperature. In the daytime and nighttime, the temperature change will be high. And this is an image which is taken pre-dawn. Then what will happen? Pre-dawn, this temperature of the alluvial fan area will be much less, and it will have the maximum radiation peak. Where? Maximum radiation peak in the longer wavelength. And that is why longer wavelength, 5 is longer wavelength, isn't it? 6 is longer wavelength, but the FCC is generated 531. So then what happens in this band? If you assign red color, then here it appears red. Similarly, in case of water bodies, in case of hard and compact rocks where thermal inertia is low, then what will happen? If thermal inertia is low, then temperature change will be less. So daytime and nighttime temperature will be similar. So that means the temperature of the rocks will be high, and because temperature is high, maximum radiation will take place in the shorter wavelength. That is why this blue, which is assigned for band 1 is where? Shorter wavelength, and temperature is high. So this is how you can interpret different rock types, different geological materials will have different response. So due to their different thermal inertia, because their density is different, specific heat is different, and because their colors are different. Color, what it does, because if the color is white, it will reflect. If the color is black, it will absorb, isn't it? So using these properties, you can characterize the geological materials. They will have different sensitivity, they will have different temperature, they will have different the maximum radiation peak, as well as their radiation will be different. So your signal strength will be different in different bands, and you can have different colors. Similarly, if you see this one, this your area, this is Mauna Loa, okay, here there are different multiple lava flows you can see, and if you see this false color composite 531, again for this case, different lava flows, basically these were erupted at different times. Basically it is a sealed volcano, isn't it? Now this these different lava flows have different temperatures. They have thermal differences. They have differences in terms of thermal inertia. Because why the differences in thermal inertia? Because they have the variation in the glassiness, variation in the surface texture, porosity, and some cases soil and vegetation. That causes different thermal inertia. And also they are erupted at different times. Some are warmer, some are cooler. Because the lava flow which has been erupted very recently will have the high temperature, whereas the lava flow which has erupted long back, this will have low temperature, isn't it? So because their temperature is different, their thermal inertia is different, so their thermal radiation will be different, and as a result you will get different temperature and different colors. Now, what are the recent advances in thermal remote sensing? Is thermal spectroscopy. It's not just single band thermal image, or it is a multispectral thermal image, but much more than that. We should be able to see this thermal spectra of the geological materials. Where is the absorption peaks? Why it is important? Because you see, geological materials are dominantly silicates, isn't it? So silicates have the characteristic absorption peaks essentially in the thermal range, this wavelength range. But we have not studied much the silicates in this thermal range. So we have studied only optical range, but optical range they do not have characteristic absorption peaks. So see here, there are different rocks like granitic rocks, cyanitic rocks, then you are getting cyanide, diorite, then basaltic rocks, and ultrabasic, donite, peridotite. These are the ultrabasic rocks, starting from the acidic family or granitic family, intermediate family, basic family, that is the basalt and your gabbros, dolerites. Okay, then to ultrabasic families like your chondrites, donites, peridotites. Okay, so then what happens? You see, very interesting. See here the emissivity spectra of these rocks. Okay, it has a low emissivity or a low this absorption peak, where at 8.6, that is here in case of granite, the absorption peak is here at 8.6, whereas if you see in case of ultrabasic rocks, it is here 10.7, isn't it? So in case of silicates, depending on the percentage of silica, if it is acidic family or granitic family, their maximum absorption peak is 8.6, whereas if it is in the ultrabasic family, their maximum absorption peak is at 10.7, and it is gradually changing from 8.6 to 10.7 as a function of silica percentage. Why? This is because this absorption band is known as the Ristretland band, and it occurs due to stretching vibration between silicon and oxygen atoms. So from this shift, you see 8.6 basically aster band 11 and 10.7 aster band 13. So depending on your radiation value or your energy radiated in band aster band 11 and aster band 13, you can make an assessment whether it is the granitic rocks, it is your cyanitic rocks, or it is basic or ultrabasic rocks. Here you see, this is very important, that not only the silicate rocks but also for clay minerals and most importantly carbonate rocks, they have characteristic absorption peaks, very narrow absorption peaks in the thermal range, but these are not well studied because we do not have these thermal spectroscopic data till date. But nowadays what we are doing using in situ spectroradiometer, FTIR. Okay, so ground based this spectroradiometer in the thermal range, we can have the spectra, and from the spectra we can characterize where is the maximum absorption peak. It may be very narrow, we can detect that because it is a continuous spectra. So this is another your emerging field. We need to have thermal this spectroscopic data, but that is not available at this moment, isn't it? Unless this in the case of this your ground based your sensor. Now you see, there is one of the most important application in thermal remote sensing is coal fire detection. Coal fire thermal anomaly due to geological cause. Similarly, there is forest fire, but that is not geological, but this is also similar kind of the importance is there. So coal fire detection, mapping, and spatiotemporal dynamics is important. See, this is this global distribution of coal fields. Okay, in different parts of the world, how the coal fields are occurring. It's a black color, you can see. And in case of India, these are the coal fields. Essentially, these are the Gondwana coal fields and these are the tertiary coal fields. So in India, there are 54 plus these Gondwana coal fields, and almost all these Gondwana coal fields are fire affected. There is a problem of coal fire, almost all. Okay. Then we need to study where this your area is fire affected, where the seam is blazing, where the seam has been affected by mine fire or coal fire. Okay, so this is an example how we do that. First, from these thermal bands, we get this radiant temperature image. This for Jharia coal field. So you get the radiant temperature image using this Planck's law. Then you get this NDVI, because from NDVI you can get this emissivity, or you can have this thermal emissivity by other means. There are other procedures available also. So from NDVI or from other procedures, you can have the thermal emissivity image, and then using thermal emissivity and this radiant temperature image, you can get the kinetic temperature image or the actual body temperature image. So this is very, very precise, and it gives you a lot of details, okay, special details. So from that, you can adopt some kind of this thermal anomaly detection algorithms, where by means of looking at how the temperature of particular pixel is different from the neighboring pixels, okay, then you can understand, you can infer that pixel has anomaly, has differences in temperature with respect to the neighboring pixels, and this temperature is higher temperature than the ambient temperature. Then you can brand this particular pixel, you can designate that particular pixel, this is an anomalous pixel, and it is potentially a coal fire pixel, because there may be other kind of high temperature these objects, like there may be brick factories or brick kiln, or there may be in case of city area, there may be urban heat island, or there may be automobiles, isn't it? So if there are a lot of automobiles are there, then there will be temperature can increase. So there are many other anthropogenic factors, okay, that may also give a particular pixel to higher temperature. But other than this, in a coal field, you can understand, you can infer, you can delineate the pixels, those are thermally anomalous and they are coal fire pixels. Now this is, you see how we have mapped it by some kind of modeling, okay, and by using certain these anomaly detection algorithms, then we have identified the coal fire pixels here. Not only coal fires, this your as a general this your thermal anomaly, but as well as whether this coal fire is a surface coal fire or it is a underground coal fire, that also we can identify by some kind of pixel integrated temperature modeling. And these are the ground truths. With that, we have compared and we have this validated our model. See here the spatial dynamics or spatio-temporal dynamics, you can see in 2005. This is the fire scenario. These are the area where surface fire, the other areas are subsurface fire. You see here, for example, in this particular area, surface fire has increased a lot, but here it was not, isn't it? If you see in this case, surface fire was high, but in this case, this is much less. Similarly here, surface and this underground fire was very, very strong in this belt. This is the name of this area is Barari, or something like this, but here you see, there is much, much less. Another area in thermal remote sensing is the surface, this your fire detection. This in case of and sub-pixel temperature detection, because the pixel size is not always very small. It is not at par the scale of the coal fire, because coal fire occurs along the seam, and the seam thickness is not very large. It may be few meters, like it may be 5 meters to 10 meters, something like this. So if it is an active seam fire, that can extend only for few meters width, isn't it? So spatial coverage is very, very small, whereas a pixel is very large, isn't it? It may be 100 meter by 100 meter. So we need to do different approaches. You can do some kind of pixel integrated temperature modeling, or you can go for this sub-pixel temperature detection. Okay, and you can go for this high temperature this pixel detection. Instead of thermal infrared band, you can go for shortwave infrared band. So these are the approaches. Here we have used shortwave infrared band and subpixel temperature detection algorithms to get this temperature of the pixel and to detect whether it is a surface fire pixel or not, and what is the temperature inside the pixel. Okay. See, these are some of the field photographs, and you see how this coal fire this occurs. Now I am going to the different applications. That is the geological hazard like volcano or lahar. Lahar is the volcanic mud flow. Okay, that is also is a dangerous in terms of hazard. A lot of casualty can happen due to lahar. Now you see in an optical image, particularly in visible band, how this volcanic cone appears very close to this volcanic eruption, very close to that, for example. And here you see in a thermal this band, you see how it appears. So these are the pixels; those are showing very high temperature. So this is perhaps the volcanic vent through which this eruption took place. So that is why here the temperature is high. Eruption has not taken place immediately before, but maybe sometimes back. So these are the pixels showing high temperature, and this area in and around the volcanic cone, the temperature is much less. But this area again temperature is high. Why? Because all the lavas were spread over that, flown over this. Okay, so that is why this area is showing the higher temperature. Now coming to another application, that is the earthquake precursor study, thermal remote sensing for earthquake precursor study. So you see, this before an earthquake occurs, there it is believed that the pressure builds up due to tectonic activities and associated your processes. So it is observed that for many of these major high magnitude earthquakes, there is a temperature increase very close to the earthquake epicenter. So very close to the earthquake epicenter, it has been observed that just before this earthquake to happen, okay, 1 day, 2 days, 3 days before, okay, it is observed that their temperature in and around that becomes high. How much high? It is observed it is up to 5 to 10 degrees Celsius temperature high in and around that earthquake epicenter. So based on that, it can be used as a potential earthquake precursor, short-term earthquake precursor. So in a few days, one earthquake is going to happen if you continuously monitor this region where earthquake, this incident's vulnerability or your possibility is high. Okay. Now you see, this is an area that is for the BAM, your earthquake in Iran, where the earthquake occurred in 26 December 2003. See, this is 22nd December in and around this is the epicenter. Okay, in and around the epicenter, thermal anomaly or a high temperature is not very high. But 23rd, you see suddenly temperature increased very close to the epicenter, and it is 24th, it is even very closer, isn't it? But if you see 25th and particularly 26th, just after earthquake happened, this is thermal, your anomaly or the temperature, increased temperature is dissipated. So this is what kind of observation was made by many of the researchers in many earthquakes globally. Similarly, in case of Bhuj earthquake in India that occurred in 2001, okay, 26 January, it was also observed the similar phenomena. See, at different times, your temperature was mapped, and you see, just before the earthquake, the temperature anomaly is very high. Temperature rises, okay, 5 to 10 degrees temperature rise was observed. But after the earthquake occurred, this temperature is dissipated. No high temperature is observed. Here you see, it is globally there are many these examples for many earthquakes. You see, this is earthquake with 7.3 magnitude, okay. Then another is 8 magnitude, is 7.1, 7.2 at different locations of the earth. There are many major earthquakes above 7 or more magnitude earthquake were studied, and it was seen that there are this prominent thermal anomaly or temperature rise was observed. So that helped us to understand that perhaps there is a relationship, and it can be used as a precursor, short-term precursor of earthquake. So with this, I stop here, thermal sensing, okay, and we'll discuss very briefly on microwave remote sensing, maybe another 15 minutes. And we'll take up the questions on thermal remote sensing today, and microwave remote sensing will take up the questions tomorrow. Okay. So to begin with, you see the microwave remote sensing. So it is different from thermal remote sensing. Thermal remote sensing was how much? The spectral range was up to 35 micrometer, isn't it? Now in case of microwave, it is from 1 millimeter to 1 meter in terms of frequency, 0.3 gigahertz to 300 gigahertz. But in case of radar remote sensing, particularly in case of synthetic aperture radar remote sensing, here the wavelengths are 1 centimeter to 60 to 70 centimeters, something like this. Okay. So you see the difference. In case of microwave radar, the wavelength is in centimeters. And in case of optical, wavelength is in micrometer. So micrometer means 10 to the power minus 6 meter, isn't it? And centimeter, 10 to the power minus 2 meter. So if you take a ratio, then what happens? Centimeter by micrometer means it is 10 to the power 4 times the wavelength. So see, you are in a different region of the electromagnetic spectrum. You are in a region where your this wavelength for this your study, or for wavelength for remote sensing, wavelength range is 10 to the power 4 times than that of optical region, isn't it? So because of this longer wavelength, definitely there will be certain advantages, definitely there will be certain this your limitation as well, isn't it? So this is one of the basic, this unique property in microwave radar remote sensing. And if you see the microwave remote sensing family, so it has passive family, it has the active remote sensing. In active, again, there is imaging microwave remote sensing by and active microwave instrument, and there may be non-imaging. Okay, so this imaging part, there is a real aperture radar or side looking airborne radar, and nowadays we are not using this real aperture radar but synthetic aperture radar. Okay, and non-imaging, there are altimeter, scatterometer. So in this particular class, we will be discussing mostly on this your active imaging radar, and most importantly active imaging radar and synthetic aperture radar in general. We will give you some examples of side looking airborne radar as well, but mostly we will be studying this synthetic aperture radar remote sensing. Why synthetic aperture radar? Because synthetic aperture, here the antenna or the aperture of the sensor is synthesized in the lab, because you cannot have a very long antenna in space. So that is why we synthesized a very long antenna. Why? Because unless the antenna size is long, our resolution is not good, particularly the azimuth resolution is not good enough in meters. In case of real aperture radar, the azimuth resolution is in kilometers. That is why real aperture radar is placed only in airborne, so that the height is not much, so that this your pixel size can be controlled to some extent, and we can have pixel of few kilometers, 2 kilometers, 5 kilometers, something like this. Whereas in case of synthetic aperture radar, we are synthesizing a very long antenna, we are getting this pixel size of few meters. Okay. Now you see, these are the advantages of the radar remote sensing, as we have also discussed yesterday. It's very sensitive to surface geometry because of its side looking geometry, and that is why this is very, very useful for geomorphology and geological structure. It is sensitive to surface roughness, so that is why it is important for this your rock type identification based on their surface roughness, particularly in terms of grain size, in terms of fracturing pattern, and that is only possible in case of non-vegetated area. Also, it is sensitive to the moisture content or dielectric property of the materials, so that helps to this characterize these geological materials based on their this your dielectric property, like unconsidered materials, like your alluvium, like your altered materials, hydrated minerals, gosans, soils, that can be this your highlighted, or that can be separated from the compact, hard compact rocks. And again, there is another very, very important advantage, is that microwave, longer wavelength microwave radar can penetrate vegetation, that means forest, and it can also penetrate ground. Because of that, in a forested area, if you use a longer wavelength this radar, so you can get the image of the terrain, you can get the image of the earth surface. And because it penetrates through ground, you can have subsurface information. For example, in case of these geological studies, like active faults in alluvium, like buried paleochannels, okay. So those kind of features are very, very important, and that can be observed in radar image, particularly where this your surface moisture is not high, like in case of arid region, in desertic region, and also in case of this your underground civil structures like water pipelines or oil pipelines, sewerage lines can also be this your identified. But in case of satellite-based radar is not much possible because it can penetrate only few meters. Ground-based radar, it is more important. Now you see these are the spectral bands. It starts from Ku, then X band 3 centimeter, then the C band, S band, L band, and P bands. And there are different satellite missions. From this beginning, I have listed for each wavelength what are the satellite missions which acquired data in that particular wavelength. There are some of the missions not yet launched, like TandemL is not yet launched. This is from JAXA, Japan. Then NISR, it is going to be launched in this 2024 early, around January, February. Okay, and it has S band and also it has L band. NISR, you can see here, NISR here, and you can see again NISR here, isn't it? So it has S band and L band, dual band. It's a great mission. Okay, it's a lot of good repeatability, very large swath, very good resolution. Okay, and a lot of applications like your deformation of the earth surface. Okay, then your cryospheric studies, then ecosystem, the forest. Okay, so there are many studies you can do with this mission, and it is a joint mission by ISRO and NASA. And there is another important mission is biomass. It is a P band, this satellite mission. It is a P band mission with a 70-meter wavelength. Okay. So this is what about the wavelength bands. Now there is the radar polarization and polarimetric SAR. Okay, so maybe I will this stop today